Good evening. Thank you for the opportunity to share our work. My name is Verónica Díaz and I'm the leader researcher at the Electrochemical Engineering Group at the School of Engineering in Montevideo, Uruguay. Today I will present a study on degradation and regeneration in PEM water electrolyzer assemblies, focusing on the combined effects of the membrane type and catalyst chemistry. The work combines results from two recent papers from our group. The presentation is organized in 5 topics. I will go briefly through motivation and methods and then spend most of time in results and conclusions. Let me start with the motivation. The context is well known but worth restating. Global warming has reached around 1.1 degrees above pre-industrial levels, and 2023 set a record of about 37 gigatons of carbon dioxide emissions. To stay within the target of the Paris Agreement and reach net zero by 2050, we need to decarbonize across all key emitting sectors, and critical for these sectors that are hard to electrify directly, we need green hydrogen. Green hydrogen is the bridge for aviation, marine transport, heavy industry, and bulk chemicals such as ammonia and methanol. And here Uruguay is in a privileged position. About 98% of our electricity comes from renewable sources, which makes us a natural candidate for the next frontier, the production of green hydrogen and its derivative at competitive cost. There are other conditions for being green hydrogen producer and exporter in our country. Apart from the high renewable potential, wind and solar PV onshore and offshore presents complementary profiles not only during the day but also during the year. Besides, our country presents institutional, legal and social stability, then has optimal logistic conditions, the coast to the Atlantic Ocean and access routes to the entire country, and last but not least, the country presents access to abundant biogenic CO2 from industrial and power plants, as well as good water resources throughout the country. This has already translated into concrete projects. There are 3 main announced projects in our country, so the technology is not longer hypothetical for us. The question is durability and cost, and that is where our research contributes. Let's now move to degradation mechanisms in PEM electrolyzers. A PEM electrolyzer is a complex electrochemical device with several components. Each component has its own degradation pathways. Briefly, on the degradation landscape, the bipolar planes suffer corrosion and embleedment. The porous transport layer can clog or lose conductivity, but the most critical component for long-term performance is the membrane electrode assembly. This assembly combines a perfluorosulfonic acid membrane, typically Nafion, with the anodic and cathodic catalyst layers. Degradation here can be mechanical, thermal, chemical, or driven by cationic contamination. And all of these end up as losses, higher potentials, higher ohmic resistance, and reduced hydrogen output. I will now describe the experimental approach. Here you can see images of the actual setup and internal structure of the cell. We built a custom electrolysis test bench with the potentiostat, galvanostat at the booster, a single cell electrolyzer, a peristaltic pump, a PID temperature controller, and the water tank. The cell explode view. From the outside inwards, the cell has a heating element, a support plate, an insulator, a unipolar plate, the flow field plate, the porous transport layer, a package, and the membrane electrode assembly itself, and the symmetric structure on the cathodic side. Membrane electrode assembly, as I mentioned, is a catalyst coat membrane with a geometric area of 25 square centimeters and a catalyst loading of 3 milligrams per square centimeters per side. The protocol was the same for both assemblies and is summarized here. It consists of 6 stages. Stage 0 is the initial baseline characterization. Stages 1 and 2 are potentiostatic degradation steps at 2 volts for a week. Stage 3 is a galvanostatic degradation step at a current density of 90 milliampere per square centimeters, also for a week. Stage 4 is the regeneration procedure, which implies the immersion of the assembly in 1 molar sulfuric acid at 80 degrees for 1 hour, following by rinsing with ultra pure water. And stage 5 is the final potentiostatic degradation step at 2 volts for another 168 hours, the week, designed to assess the durability of the regeneration. Between every stage, we perform the full electrochemical characterization sequence, cyclic voltammetric, linear Schwab voltammetric, and impedance. This allows direct stage-by-stage comparison of degradation, recovery, and we will now go through the results in 2 blocks. The first block corresponds to our first study published in Electrochemical Acta in 2024. In this study, we use a membrane electrode assembly based on Nafion 1110, a thick membrane with 254 micrometers, with platinum black as the catalyst on both the anode and the cathode, with a loading of 3 milligrams per square centimeters per side. Under potentiostatic operation, the current density falls rapidly at the start of stage 1 and then reach degradation rate of about 250 micrograms per hour per square centimeter. After stage 3, we apply the acid treatment. The result is striking. In stage 5, the post-regeneration degradation rate drops to about 40 micrograms per hour per square centimeters, 6 times lower than before regeneration. The idea during the regeneration step is to reprotonate the Nafion and remove cationic contaminants that have accumulated during operation. When we compare all potentiostatic stages together, the picture becomes very clear. The regenerated assembly degrades much more slowly than the original assembly did in stage 1, confirming that the acid treatment successfully restored most of the active sites. Well, let's go through the polarization curves. Here, this figure depicts the polarization curve for the baseline and the degradation steps 1, 2, and 3. it is clearly how performance deteriorates and the curve shifts toward higher potential during the degradation. In this figure, we can see the effect of the regeneration treatment. The curve in stage 4 recover partially the performance at the baseline stage. This tells us that most of the performance loss in the Nafion 1110 assembly was due to reversible contamination that sulfuric acid can wash out. And after stage 5, the post-regeneration potentiostatic degradation step, the curve only slightly degrades from the regenerated condition. The fact that some performance is not recovered tells us there is also an irreversible component of degradation, which we will see more clearly in the impedance data. To separate the different contributions, we feed the ACE spectra to equivalent circuits at 2 operating points, 1.9 volts and 2.3 volts. 1.9 volt, where the response is controlled by activation of a potential, we use a simple circuit with 2 resistant constant phase element branches, one for the cathodic charge transfer and one for the anodic charge transfer in series with the ohmic resistance and the inductance. This figure presents the Nyquist plots at 1.9 volts. We can clearly see the growth in the semicycles with respect to the baseline, indicating an increase in charge transfer resistance. Between the baseline and stage 3 plots, we can also clearly see an increase in ohmic resistance. This slide shows again how the 2 depressed semicycles grow markedly with degradation, and after regeneration the semicycles collapse back to almost the pristine stage in agreement with the cinetic recovery of the catalyst. 2.3 volts, the situation is different. Here we feed with a resistant constant phase element branch to account for the mass transfer or diffusion process. This slide presents the overall trend at 2.3 volts, and here we can see the low frequency mass transfer feature that grows substantially with degradation, especially after stage 3, and decrease markedly after the regeneration treatment. We plot the ohmic resistance as a function of stage. We see a small increase during stages 1 and 2, a sharp jump after stage 3. The ohmic resistance remains elevated throughout stages 4 and 5. This is our first signature of irreversible degradation. The ohmic resistance is controlled by the protonic conductivity of the membrane and the contact resistance between catalyst, binder, and membrane. The fact that it doesn't recover even with acid treatment indicates that the Nafion 1110 membrane itself has suffered structural degradation. This is the fingerprint of irreversible damage to the membrane itself. This is consistent with our water analysis. We measure 1.5 milligram per liter of fluoride in the effluent after the experiment. Fluoride release is a classical signature of chemical attack on membranes. This chemical attack is due reactive oxygen species like hydrogen peroxide formed by gas crossover. So for Nafion 1110 assembly, the kinetic are largely reversible, but the membrane is being chemical adapted. The cathodic charge transfer time constant grows during degradation and then drops sharply after regeneration, almost to pristine values. This is the kinetic recovery I mentioned. The drop is most marked precisely at the cathode, compatible with the removal of reduced impurity by the acid treatment. The anodic time constant shows a similar behavior. And the mass transfer time constant, only meaningful at 2.3 volts, increases through stages 1, 2, and 3, indicating that transport limitations become progressively worse. So, in summary, for the Nafion 1110 assembly, the kinetic and contamination related losses are largely reversible by acid treatment, but the ohmic and structure losses are not, and the membrane is being chemical attacked, as evidenced by the fluoride emission. Brings us to our second study, recently published in Fuel. In this work, we use a second assembly with Nafion 115, about half the thickness of the Nafion 1110, keeping platinum black at the cathode, but using iridium-ruthenium mixed oxide at the anode. 2-volt potentiostatic operation. The degradation rate is about 204 micron per hour per square centimeter, already lower than the Nafion 1110 degradation rate. The galvanostatic stage requires only about 50 millivolts of additional voltage over the wick, comparable to the first assembly. But the post-regeneration behavior is very different. In stage 5, the degradation rate accelerates to 860 micron per hour per square centimeters, more than 20 times faster than for the regenerated Nafion 1110 assembly. So regeneration recovers performance, but the recovery doesn't last. This figure shows the polarization curves during all these stages. The behavior up to the regeneration step was similar to the first assembly. Curves shift toward higher potential, but the post-regeneration behavior is very different. After stage 4, the polarization curve actually slightly exceeds the original baseline. We attribute this to the acid acting as a post-synthetic activation step on a partially activated commercial membrane electrode assembly. The impedance analysis, we use a slightly more complex equivalent circuit with 3 resistance constant phase element branches in series with the ohmic resistance and the inductance. We assign the 3 branches to cathodic charge transfer, anodic charge transfer, and a low frequency feature dominated by mass transport and gas evolution dynamics. I want to stress that this assignment is qualitative. In PEM water electrolyzers, anode kinetics and gas evolution features often overlap in the low frequency region. Resistance increases from stage 0 to stage 3 as expected, and then keeps constant around 29 milliohms in the latter stages. And here is the most important point of comparison. When we measure fluoride in the effluent at the end of the Nafion 115 campaign, the result was below the detection limit. So even though this membrane is thinner, the iridium ruthenium oxide anode suppresses the formation of reactive oxygen species and protects the polymer backbone from chemical attack. Both time constant associated with charge transfer processes peak at stage 3 and decrease after regeneration. Kinetic recovery is real and visible. The mass transport related time constant grows through all stages and at 2.3 volt reaches its maximum at stage 5. This is a different signature. It tells us that even after regeneration, the transport pathway continues to degrade. We now summarize the main conclusions. First, under potentiostatic operation, the Nafion 1110 with platinum black assembly degrade at about 250 micron per hour per square centimeters, while the Nafion 115 with iridium ruthenium oxide assembly degrade at about 204 micron per hour per square centimeters. Under galvanostatic operation, we observe voltage drift rates at about 130 to 268 microvolts per hour. Second, fluoride emission tells us a very clear story about chemical degradation. Only the Nafion 1110 assembly clear evidence a chemical attack of the polymer backbone. So the iridium ruthenium oxide anode catalyst provides effective protection against oxidative chemical degradation of the membrane, even though this membrane is thinner. Third, the regeneration procedure with sulfuric acid is effective, but its durability depends strongly on the assembly. For the Nafion 1110 assembly, the post-regeneration degradation rate dropped to 40 micron per hour per square centimeters, 6 times lower than before. But for Nafion 115 assembly, the post-regeneration rate accelerated to 860 micron per hour per square centimeter, meaning that while acid treatment recovers initial performance, it does not stop cumulative structure damage at the anode. Taken together, our results shows that PEM electrolyzer degradation has a dual nature, a reversible component, mainly contamination and protonation effects that acid regeneration can recover, and an irreversible component that progresses regardless of the regeneration. I would like to acknowledge the support of Ceci Kudelar, Pedesiva and Ani, as well as my co-authors. Thank you very much for your attention. I will be glad to take any questions.